In this video, I'll be proving the value of this infinite sum, which is 17 over 75 times 76 plus 17 times 18 over 75 times 76 times 77 plus 17 times 18 times 19 over 75 times 76 times 77 times 78 plus so on and so forth, where on the top you're just incrementing by 1, multiplying by that each time, and on the bottom you're incrementing by 1, multiplying each time. Black Pen, Red Pen gave me this problem in an email, so shout out to him for giving me the problem and the video idea. So how should we start with figuring out this value? Well, it would probably help if we could figure out a formula for the numerator and a separate formula for the denominator. So let's go ahead and do that. So what should the formula for the numerator be? And I'll be assuming we're starting at n equals 0. So at n equals 0, we want the value to be 17. And then in the next value, we want it to be 17 times 18. And then at the next value, n equals 2, we want it to be 17 times 18 times 19. And I hope you can see the similarities of this and the factorial function. And so, because we want to start at 17, we should probably do n plus 17 factorial, right? Because at n equals 0, what will we have? We'll have, well, 17 factorial. At n equals 1, what will we have? Well, we'll have 18 factorial, or 17 plus 1 factorial, which is the same as 18 times 17 factorial. And then at n equals 2, what will we have? Well, we'll have 19 factorial, which is 19 times 18 times 17 factorial. Now you can already see the similarities here, and you can see that we're getting the right values for what we're multiplying it by, but we're not getting 17, we're getting 17 factorial. So now what I'm going to actually do is expand 17 factorial out a little more into 17 times 16 factorial. So this is another way of writing 17 factorial. Right here are the values we want. Those are the values that we want out of this, and every single one is just multiplied by 16 factorial. And so the formula would just be n plus 17 factorial, and then you divide out by 16 factorial to get rid of it. And that's exactly what we're going to do, is we're simply going to just do over 16 factorial. So the final formula is n plus 17 factorial divided by 16 factorial. And that's the numerator's formula. What's the denominator's formula? Well, it's going to be very similar. So the first value you want is 75 times 76. The second value at n equals 1 that you want is 75 times 76 times 77. At n equals 2, you'd want 75 times 76 times 77 times 78. Very, very similar idea. So I'm going to choose to do n plus 75 because we start with a 75, right? So that would make the most sense. So we'd have n plus 75 factorial. Except this does not work, because if I plug in n equals 0, what do I get? Well, I would get 75 factorial, because it's n equals 0. There's no 76 in the midst of this 75 factorial. There's only a 75, a 74, a 73, all the way down until 1. 76 is nowhere to be found in this entire thing. However, what we could do is just increment this to be 76 factorial. Because then what would happen? So n plus 76 factorial. When you plug in n equals 0, you would get 76 factorial, which is 76 times 75 times 74 factorial, right? And then if I plug in n equals 1, I would get 77 factorial, which is the same as 77 times 76 times 75 times 74 factorial. And then for n equals 2, you get the idea, is 78 factorial is the same as 78 times 77 times 76 times 75 times 74 factorial. Well, look at that. Right here is everything we need. What we should do is just erase that 74 factorial by simply dividing by it. So just divide it by 74 factorial. Because it's multiplication, you cancel out with division. So now that we've spent all that time figuring out the formula for the denominator and the numerator, let's go ahead and put this into one compact summation. So again, we start at 0. So we do the sum from n equals 0 to infinity. Well, we should start with the numerator formula, which is... And then we do this formula, all of that over this, which is the formula for the denominator. And so we have the numerator on the top, the denominator on the bottom. What do we do with this? Well, it would make the most sense if we do the reciprocal of the bottom and multiply it, like fraction division. So we have n plus 17 factorial divided by 16 factorial times, well, that's 74 factorial over n plus 76 factorial, which is then equal to, well, the 74 factorial and the 1 over 16 factorial are just constants, so I can move them out like this. So 74 factorial over 16 factorial times the entire summation, n equals 0 to infinity of, well, those are gone. Let's just combine these two into one fraction. N plus 17 factorial over n plus 76 factorial. I'm now going to simplify this. Well, simplify. I'm actually going to expand this and then simplify. And you'll see why I'll do that in a moment. So we'll do 74 factorial over 16 factorial. I'm not going to do anything with this. I'm just going to leave it written like that for now. Okay, the sum from n equals 0 to infinity of, let's just go ahead and write each of these out individually. So n plus 17 times n plus 16, multiplied all the way down until 1. And then all of that is over n plus 76 times n plus 75, all the way down, and then eventually we will reach n plus 17 times n plus 16 times all the way down into 1, and then you see we cancel all of these out with each other. And what you'll be left with on the bottom is what comes before in this multiplication, n plus 17. Well, we'll just end on n plus 18 on the bottom. That's what comes directly before n plus 17 in the denominator. And then on the top, everything has just been canceled out, so they all go to 1. What I'm going to do is actually shift this summation in a way that'll make it easier in the future. So I'll do this sum from n equals 18 to infinity. Why would I do that? Well, it's to make this just n, because at n equals 0, the value of n plus 18 is going to be 18. At n equals 1, the value at n plus 18 is going to be 19. So if I shift it to n equals 18, instead of starting at n equals 0, well, what do I get? Well, at the starting position, n equals 18, the value of n is going to be 18. At n equals 19, the value of n is going to be 19, so on and so forth. They agree, and so this was just to make that n plus 18 just an n. Now everything shifts in a similar way. So we started with n plus 18. What I'm going to do is just subtract 18 from it, and that's how I got n from that. And so this is going to be n times, well, the next one in the sequence going backwards in the multiplication would be n plus 19, which is going to get n plus 1 next. So we'll have n times n plus 1, so on and so forth, going all the way up until the end of this sequence, which is now n plus 76. So n plus 76 minus 18. 76 minus 18 is 58. Yeah, so it's 58. So right there at the end, we'll have n plus 58. Now, what was the point of translating it like this? Well, it's so that I can write it out in a different way. So it's going to be 74 factorial over 16 factorial times, what's it going to be now? Well, it's going to be the sum from n equals 1 to infinity of this same thing, except I can't just do that. I can't just change the lower bound out of nowhere. There's a bunch of extra terms. There's the terms n equals 1, which wasn't there before because it started at 18. There's the term n equals 2, n equals 3, all the way up until n equals 17. Those are all the terms that are in this new sum that weren't in the previous. And so what I'll do is I'll just subtract those terms off. Subtracting all of these terms at once will be the same as subtracting their sum. So this is the sum from, well, we start at n equals 1, and we go up until n equals 17. Sum of all of those, and then same exact formula inside. So this is the final formula that I'll be evaluating. I'm going to erase all of this, so if you haven't already, try to understand what's on the board right now. Alright, this is the formula I'll be working with, and why would I want to work with this formula? It looks so much worse than what we had before. The reason I want to work with this is because both of these summations are in a form which is easily evaluated. Now I'm going to be proving a pretty general theorem here that you can use a lot more often than just in this context. The sum from n equals 1 until m of 1 over, now I'll be mimicking this sort of pattern. So it'll be the multiplication of n times n plus 1 all the way up until, well, I want it to be general, so it's going to be n plus a. And this a is an integer which is bigger than or equal to 2. Now, how on earth would I evaluate this? Well, I'm going to prove to you that it's equal to 1 over a times a factorial minus 1 over a times m plus 1 all the way up until m plus a. Now, am I just going to pull this out of my buttocks? Yes, because I just loosely based it around a similar formula, which is the sum from n equals 1 until m of 1 over n times n plus 1, which is in fact equal to 1 minus 1 over m plus 1. Because if I do n equals 1, if I plug that in, I get 1 over 2. If I plug in here, I get 1 over 2. If I plug in n equals 2 into here, I'd get 1 over 6, which is then equal to, well, 2/3. Alright, if I plug into here, I get 1 minus 1 over 2 plus 1 is 1/3. 1 minus 1/3 is 2/3. And similarly, if I were to continue this to plugging in n equals 3, I'd get 1 over 12, which is then going to be equal to 3/4. If I plug in m equals 3, which is the number of terms, m equals 3 into this formula, I'd get 1 over 3 plus 1, 1 over 4. 1 minus 1 over 4 is 3 over 4. So that formula works, and I'll go ahead and prove how it works using this extended formula. So this case is a equals 1. So let's plug it into this general formula. It's 1 over 1 times 1 factorial minus 1 over 1 times m plus 1. Do I need to go up any further? No, because it's m plus a. So this is the formula we get out, which is 1 minus 1 over m plus 1. Now, this is just loosely how I came up with the formula. I actually just plugged in a bunch of numbers into Wolfram Alpha and found a pattern, and then went back and proved that pattern. So what I'll do is I'll prove it using induction, which always works. So we start with the initial case, which is m equals 1, which is the sum from n equals 1 to 1 of whatever, which is just a single term plugging in n equals 1. Let's go ahead and plug in n equals 1. So we'd get 1 over 1 times 1 plus 1 times, well, 1 plus 2, all the way up until 1 plus a. This, on the bottom, is just a plus 1 factorial. You can clearly see that. So this is equal to 1 over a plus 1 factorial. All right, let's go ahead and compare this with plugging it into the formula. So plugging it into the formula, I'd have 1 over a times a factorial minus 1 over, well, I'll have a times, what's the value of m? Well, it's 1. So I'll have 1 plus 1 times 1 plus 2, all the way up until 1 plus a. I hope you can see the beauty of all of this, because I can go ahead and add in a little something here. I'll add in a term of 1 times. 1 times anything is itself, so we don't have to worry about it. This is 1 times 2 times 3, all the way up until 1 plus a. And so what's there on the bottom is a plus 1 factorial. So we have 1 over a times a factorial minus 1 over a plus 1 factorial. Except, there's still this a out front. Now you can probably already see the similarities here, but I'll go ahead and make them even more apparent by moving this a right here to the front, and then splitting a plus 1 factorial into a plus 1 times a factorial. Now what do you see? Well, you see that these are really the same thing, except this one does not have an a plus 1. So let's go ahead and multiply the top and bottom by a plus 1, right? Now you can see they have the same denominator, so now we can just subtract the numerators and combine them. So we'll have a plus 1 minus 1 over a times a plus 1 times a factorial. Now you can see a plus 1 minus 1 is just a. And then we have these two a's. Those cancel out to become just 1. And so we get out the other end. 1 over a plus 1 times a factorial is just a plus 1 factorial. And so in this long-winded proof, you see we get the same value from the formula as we did from the actual partial sum. And so what this tells you is in induction, the initial case is satisfied. Now, the next thing you have to do in induction is prove that if you assume m, that means that it's also true of m plus 1. Let's go ahead and do that. So we have
the sum from n equals 0 to m of 1 over n times n plus 1 all the way up until n plus a is equal to that formula. 1 over a times a factorial minus 1 over a times n plus 1 up.
Alright, now let's go ahead and analyze the sum from n equals 0 until m plus 1. So we assume that this is true. Now we're going to prove this. So it's of 1 over n times n plus 1 all the way up until n plus a What you should note is that these partial sums I can split up into the sum from n equals 0 until m. Very clearly, this is going to be important, of 1 over n times n plus 1 all the way up until n plus a. And then I add on the term that I removed from this sum, which is the value at m plus 1. What's its value at m plus 1? Well, it's 1 over, plug in n equals m plus 1, you get m plus 1 times m plus 2, all the way up until m plus a plus 1. Now we can replace this first partial sum with its value with the formula, which is
1 over a times a factorial minus 1 over a times m plus 1 all the way up until m plus a.
Alright, and then on that, we're adding 1 over
m plus 1 times m plus 2 all the way up until m plus a plus 1.
You can see there are two differences between these. With this one, it's missing m plus a plus 1. With this one, it's missing a. And so what we'll do is I'll multiply the top and bottom of this one by a, and I'll multiply the top and bottom of this one by m plus a plus 1. And now they have the same denominator, and we can look at them combined. So we'll have 1 over a times a factorial. Because this is minus, I'll write it the other way around. So we'll have plus a minus, well, on the top we'll have m plus a plus 1, and then over the common denominator, which is
a times m plus 1 all the way up until m plus a plus 1.
You can see that if I distribute that negative into all of these, that we have an a and we have a minus a, which cancel out. And then what are we left with? Well, we're left with minus m minus 1, which again is equal to negative m plus 1, because that's minus m minus 1 when you distribute it in. And now you can see there's an m plus 1 on the bottom and m plus 1 on the top. We cancel them out to 1, and so we get 1 over a times a factorial. We still have the minus, so it's a minus. Now that's a 1 on top because it canceled. A times m plus 2, which I'll actually write as m plus 1 all the way up until m plus a plus 1 is the same as m plus 1 plus a. And now you can see that in assuming m, this formula still holds for m plus 1. It's 1 over a times m plus 1 all the way up until m plus 1 plus a, and that is the formula if you were to plug in m plus 1. And so we verified it. This is the inductive step, this is the initial case, and so it's true for all m bigger than or equal to 1. That's how induction works. Now, let's go ahead and figure out what the sum from n equals 1 until infinity of this big thing is going to be. Alright, so we have this big sum, and it's from n equals 1 to infinity. We have the partial sum formula, and so we just do the limit as m approaches infinity of the sum from n equals 1 until m of 1. And again, right there we have a formula for that. This is the limit as m goes to infinity of, let's put in the formula there,
1 over a times a factorial minus 1 over a times m plus 1 all the way up until m plus a.
Look at that. Right here, this has no m's. It's a constant. So that just comes out the other side unscathed. Now what about this? Well, every single m is in the bottom, and m is going to infinity. And so all of this on the bottom is going to infinity. That's all infinity on the bottom. We have 1 over infinity, which is 0, and so this term just goes away in the limit. It all goes to 0. And so out the other end, we get this beautiful, beautiful, simple answer for this, what appears to be complicated sum. Now let's go ahead and evaluate the sum that we originally had. So we get 74 factorial over 16 factorial. This sum from n equals 1 to infinity is the case where a is equal to 58. And so we have 1 over 58 times 58 factorial. All right? Then we have to subtract off this one right here. A is still 58, so it's 1 over 58 times 58 factorial. And then we have to subtract off this part of the partial sum formula, which will feed into there, which is then 1 over, we have a 58 times, m is, what is m? Well, it's 17 right here. So 17 plus 1 all the way up until 17 plus 58, which it says 1758, really. That's the number that comes out of there. I didn't do this problem beforehand. I knew how to do it. And that's pretty funny. All right. So we have a minus 1 over 58 times 58 factorial and a plus 1 over 58 times all that. And right there, we have the positive version and then minus it. Those cancel each other out. And what do we get out the other side? Well, we get 74 factorial over 16 factorial times the only thing that's left, which is 1 over 58 times, this is going to be 18 multiplied all the way up until, what's 17 plus 58? Well, it's going to be 75. Let me go ahead and write out 74 factorial. So it's 74 times 73 all the way down until 18 times 17 factorial. All right? Just write 17 factorial for the trail that's at the end. All right? You can see that all of these terms, all the way up until 70, let me go ahead and write it out. It's all the way up until 74, and then there's an extra 75 out the other end. Those all cancel with this. And what we're left with is, on the top, you'll have a 17 factorial. On the bottom, you'll have a 16 factorial. Over here, you'll have a 1 over 58 times 75. Those were the only things left. As you can see right here, that will just give you 17 times 1 over 58 times 75. Let me go ahead and get out my calculator. It is going to be 17 over 4,350. And that is the final answer. Comes out after all of that. And that's it.